Hi, folks. Dr. Matt Moynihan here. Got some questions from the internet regarding the Fusion Masterclass that I was emailed. And so I thought I'd do a question and answer series. The goal is to try to get this information out as fast as possible. I actually made a mistake in the bad ideas lecture where I stated that ion beam target ICF was the issue there is that ICF is a shock-driven process, and the beams are essentially creating the shock wave in the target. So supporters would argue that ICF shocks are different than a beam target system because they're saying, hey, ion beam hits the surface of the target, and that creates the shock wave, and it's the shock wave that does the compression and the fusion and all of that. And so the ion beam is just a driver. And so because of that, ion beam driven ICF does not fall into the pit of a beam target system. So that was a big mistake. And I pulled back the video and I'm trying to edit it now to fix that. So sorry to all the ion beam ICF supporters out there. Okay, so let's get to the questions. The first one was, why isn't there a Mobius strip single-turn Stellarator design? It seems like that would be the simplest geometry because it gets the plasma to turn over and over and spend equal amounts of time turning left and right. So the Stellarator itself is an optimization problem. What the problem is trying to overcome is that in a plasma, the ions and the electrons have different masses. Ions are big, fat, heavy. They move more slowly than electrons. And so when you have the whole plasma turn around a corner in a Tokamak or in a Stellarator, the ions will move faster and they'll move towards the outside quicker than the electrons. I had that backwards. The electrons move to the outside faster because they're lighter. The ions would stay closer into the center because they're heavier. And that creates electrostatic problems, right? Because you got positive charge in one place, negative charge in another place, and you kind of break quasi-equilibrium a little bit. You create these instabilities that can cause problems. So the Stellarator tries to beat this back by having a twist where the plasma gets pushed outward and then gets pushed inward. And there's a frequency to how that behavior occurs. Just like plasma has an Alfvén wave that has a natural frequency, there's a frequency to this kind of twist that occurs in a Stellarator. And that plasma frequency and the magnetic field and the plasma density all kind of play into that. But that's what drives the shape of the reactor. You see, so it's not the reactor itself driving what the plasma does. It's the other way around. The plasma behaves the way it's going to behave based off of a combination of density, temperature, magnetic field, and other things, other considerations. So it's going to do what it wants to do. And so you're naturally building the reactor around the natural movement of the plasma, if that makes any sense. So I hope that answers your question. So the second question is, does Todd Ryders' paper make significant claims about Tokamaks or Stellarators? I mean, if it does shoot down a bunch of concepts, are these included in that? And why would they be included in that? So just to back up, so Todd Ryders' work was at MIT in the mid-90s. He published 2 papers and a thesis. And the papers analyzed plasma fusion reactors where the plasma was not at thermodynamic equilibrium, aka like a Maxwellian bell curve or a thermal distribution of plasma. So his systems were not at those conditions. And he basically said that they would fall into those conditions due to natural processes. So the plasma charges would mix together and the thing would become unstructured and it would become essentially a blob, an unstructured, homogeneous, uniformly mixed blob of plasma in the center of a reactor that radiates a ton of energy away. And then he modeled the blob using a set of two fluid equations, which is a model framework where you have the electrons and the ions. They're both fluids. They both kind of occupy the same space. And then you have this math term that kind of accounts for how they would they interact with each other. Two fluid models, by the way, was probably the state of the art for theory in the late 80s, early 90s for plasma physics. And it's the basis for the NRL plasma formulary, if you're wondering. So if you have that formulary, it's a famous little book. You can get it online for free. You can order it from the Naval Research Laboratories in the United States. That little book has all these equations kind of spelled out, and it's essentially the two-fluid model. So Ryder has this blob of plasma, virtual theoretical blob of plasma. He applies these two fluid equations, and he comes out with all these statements about reactors that have that kind of plasma and how they won't work because they radiate a ton of energy away, and so they can't be held hot enough. Which, by the way, I think is pretty theoretical, probably needs to be revisited, had a lot of question marks around things. And at the time, that analysis, if that analysis was redone today with modern computing, modern simulations, and a much clearer understanding of plasma instabilities, probably would yield a lot more insights. And somebody should do that. Somebody should really revisit Ryder's work 30 years later. But anyway, he didn't make statements about Tokamaks or Stellarators because those systems are at thermodynamic equilibrium. And moreover, those systems don't have blob-like plasma. So if you just, for instance, just look at the plasma in a tokamak, it's structured, all right? Because the magnetic field inside a tokamak permeates the entire plasma and kind of holds it together at the same time. So that's a structure, right? That's a structure inside a plasma. Stellarator is the same thing. It's got a plasma field that goes through the whole thing and kind of makes it structured and kind of keeps it in one place. So it's not a blob. It's not it's a thermodynamic equilibrium, but it's not a blob. So it wouldn't be necessarily subject to all the things that Ryder claims. Ryder was, when he wrote this paper in the mid-90s, he was trying to shoot down a concept called the polywell, and it ended up making related claims about a series of other approaches in the plasma structure world that honestly today may not even hold up, because, today TAE Technologies, in October 2021 came out with a paper that said we can heat plasma ions to 5 million degrees Kelvin in our plasma structure. And I don't know if Ryder would have agreed that would have been physically possible based on his theoretical work done in the mid-90s. But now today we know that that's possible because we've seen it happen. We got a private company that can do it routinely. They can turn on their machine and get their plasma that hot. So it would be interesting to revisit Ryder 30 years later with modern tools and take another look at all his stuff, especially given the advances in the modeling techniques. And two-fluid model is not the best thing that we have now. We have much better, more granular microturbulence type models that you could use on high-performance computing platforms to do better simulations of all this stuff. So just to answer the question shortly, it doesn't make statements about those two approaches because they are at thermodynamic equilibrium, and so Ryder's analysis doesn't really apply. So the next question is, can you clarify what you mean by the wrong kind of neutrons and the right kind of neutrons? Please elaborate. So there is a historical example of this happening in fusion history. And it comes from the late 1950s, right before Scalia 1 demonstrated fusion in a building using a theta pinch system. The British had a machine called Zeta. And Zeta was a large pinch machine being built and used at Culham in the UK. And the British measured neutrons coming off of that device, and they rushed to the press to claim that these neutrons were from a fusion reaction. And they did that probably because they were under pressure from their government to show evidence of fusion, and they were in a race with the Russians and the Americans to get there first. So in the enthusiasm and maybe from pressure from politicians and folks over their heads, scientists announced that they had fusion earlier than they actually did. And it was only later that they measured the energy spread of the neutrons and determined that those neutrons could not have come from a fusion reaction. So a deuterium-deuterium reaction creates a neutron with a very specific energy spread. You can look it up on Wikipedia. If it's deuterium-tritium, there's also specific energy spread, plus there's a 14 MeV neutron coming off. So you've got to have neutrons of the right energy to indicate that the right physical mechanism occurred. Now, what other mechanisms generate neutrons? I mean, there's natural neutrons that'll come off of radioactive material or activated material. So if you have a bunch of metal that's undergone radiation, it can become radioactive with time, and then it can give off neutrons. But those would be low energy neutrons, not high energy neutrons that would come from a fusion reaction. So measuring the energy of neutrons, there's a diagnostic for this. There's three ways to measure neutrons. There's gamma detection or gamma Geiger counters. Geiger counters. And if you buy them, you can get them online. And one of the best ones are the ones from the 1950s in the United States. They're yellow, and they were made by the Atomic Energy Commission. And they were actually pretty popular back in the 1950s because everybody was worried about nuclear bombs, and so people had them in their homes and things. But those things are still kicking around, and they're excellent, reliable products. They don't fail, they don't break. You can use them easily. There's also activated silver. So you put a block of silver into the reactor, and the fusion event would create a radiation that would hit the silver and make it radioactive. So it's essentially you put the block of silver in and you put the Geiger counter on it, and then when the silver itself gives off radiation and makes the Geiger counter click over, that means that a fusion event has occurred. And it's one of the more reliable ways to determine if a fusion event has occurred, because to activate the silver, the radiation has to be the appropriate energy from a fusion reaction. You can't just get inadvertent neutrons won't have enough energy to activate silver, but activated silver is like a pretty robust way to determine that a fusion event occurred. And of course, the third way is the bubble chamber. You put a bubble chamber next to fusing plasma, and it's a cheap, simple, easy way. You can buy them off the shelf. What happens is the neutron actually, when it leaves the fusing plasma, it'll fly through the goo in the bubble chamber, and it will lead a track of bubbles as it passes through that it created. So 3 different methods to determine neutrons, and of the 3 of them, activated silver is the most reliable, because of it can only work when the neutrons have enough energy from a fusion event. So those are how you measure neutrons from a fusion reaction. And in the case of Zeta, they may have used those 3 methods. They probably used a 4th, more scientific method. You can do things like sheets of material, and you have neutrons penetrate those materials, leading to a measurement of the energy spread on the neutrons. The next question is, can you clarify the issues around transporting a beam from point A to point B, and why they naturally don't want to move from point A to point B? I don't really understand what this means exactly. So ion beam systems have fundamental flaws because beams of ions don't want to stay coherent. If you have a bunch of positives that are moving together across a space, they're gonna reject each other, and then it's gonna force them to spread out in time. So ion beam systems suffer from that, and there are a variety of methods to try to keep the beams together, and there are tricks around that as well. So a method to keep it together might be electrostatic refocusing. So in the mass spec world, you'd send a beam through an electrostatic field created by an electrode, and that would force the beam to recondense. So a beam, a beam of positive ions doesn't actually look like a beam. It looks like almost like a flashlight sort of spread. It would spread out, hit the lens, and then refocus, and then it would spread out again because the positives don't like each other. So then you have to have another lens that refocuses them, and then they spread out again, and then another lens that refocuses them. And you can kind of go through this process. So the beam doesn't really travel very easily from point A to point B in one straight line like a laser beam would, because the ions have those charges. They want to spread out. And you have to keep refocusing them to keep them together and coherent and get them from point A to point B. All of that takes a lot of energy to drive all that. And that's that places the ceiling on ion beam systems that you have to overcome. Now, as I said earlier, there's also tricks. So in the mass spec world, they observed, for example, ion beams that would naturally bunch together in these conditions. And one fusion company in Boston in 2009 tried to build a fusion reactor based off of that concept. So they tried to naturally bunch the ions together and maybe take that effect to 11 and see if they could get a fusion power plant out of that. So those problems of keeping the ion beams together plagues all these ion beam approaches. And I'm not saying that it's a killer, because it's not necessarily a killer, but it's a problem that everybody has to deal with if you're doing ion beam type systems. Now, I will say also that TAE has pioneered this use of particle accelerators, so they can take an ion from a resting position and speed it way the heck up quickly and in a short distance and time frame very efficiently. And then that gets the ion really, really hot, and then they inject it into the spinning plasma structure that keeps it spinning around the outside. So if I was going to look at what's the state of the art for ion beam systems and how far has the technology come in overcoming this problem from keeping beams coherent as they move around a space, I would look at TAE. I would look at what they've built, and I would say, okay, so this is probably the best that the field can do right now. How good is this? Is this good enough to make ion beam driven ICF or beam target systems, fusion systems of interest to the private community? So food for thought there. So the next question is on thermal power plant efficiency. So the viewer points out that a typical power plant efficiencies are 40 to 50%, and I don't know of any system that can achieve 60% with thermal technology. And that actually may be true. On efficiencies, when I went to school, we were told as chemical engineers that the efficiency of a power plant was 25%. 25% to 30%, and you couldn't do better than that for a variety of reasons and thermal reasons. But that has most certainly changed out in industry. The world record for efficiency in a natural gas plant is above 60%. There's a German plant, a Siemens German plant in Europe that brags about this. There's a great video on the internet where they talk about 60 to 60, I think it's 61 or 62% efficiency for overall energy capture. But that very well might not be just thermal. There may be additional processes that they've built to capture energy off a natural gas reaction. So it's worth taking a look at that. Fusion, you would expect fusion to not have great efficiency from the start because it's the first time it's been used. But that said, there's a lot of innovative ways to capture power from a fusion power plant that show a lot of promise. I mean, direct conversion is one. You take the hot helium atoms that are coming off a fusion reaction. They come off at 3 million volts roughly, and you fire them into a piece of metal, and that holds the metal consistent and steady, and it drives current elsewhere in the circuit. The traveling wave tube is one that Eric Lerner and the dense plasma focus crowd has promoted, and that's where you basically pass those charged particles that are coming off a fusion reaction around in through a tube with a wire on the outside, and then the voltage wake draws electrical current as it moves forward. The radioisotope batteries, nuclear batteries, use two different metals, and then you have heat applied to them, and that draws a current using something called the Seebeck effect. And so fusion could use something similar. Now, best Seebeck effects right now are about 10% efficiency for capture. So traveling wave tube, direct conversion, Seebeck effect. Also, just the traditional thermal blanket, right? The neutrons and the heat going into a thermal blanket, and then that's the primary loop going to heat exchanger, which then turns steam. And if my money was on something, I'd bet the thermal thing, because it's just so widely proved, it's so robust, so well understood. But it's not to say that these other innovative energy capture approaches would work. And again, fusion is a unique power source in that the energy coming off is hot, high potential energy atoms. You have these unique energy capture approaches that only work for fusion. They don't work for fission. They don't work for natural gas plants. They don't work for coal plants. And so fusion gives you a unique set of outputs. You can couple that with the unique energy capture approach and get a really cool efficiency. So it's an innovative technology area. And but to the viewer's point, I think I would agree. I don't know about efficiency plants for thermals. I do know that there's a natural gas plant with over 60% efficiency. Not sure if that's all thermal or what that all is. So next question. I've heard this explanation for the Dynamaxx several times, and I don't get it still. What is injected helicity? Is it just a helical magnetic field? And why is the word injection used? Well, I don't say it's a toroid field like a tokamak, but is injected. So please clarify what a Dynomak is basically what the viewer was asking. So I may not have covered it well. And I'm not, Derek Sutherland is a better person to answer about what a Dynomak is exactly. So, I mean, whatever he says, I would defer to him since he's running the company and has been studying it for his PhD. But you have a plasma structure that's formed. And that's essentially a plasma donut. It's plasma racing around in a circle. And as it races around, it creates a magnetic field perpendicular to it. So if you imagine it, I hope I'm showing a picture of this. You got the current going around in a donut, plasma going around in a donut. You got a magnetic field around the outside, 90 degrees, stabilizing that donut. Now, the Dynomak applies an electric field on the corners. And by doing that, it can twist the internal field. And it twists it, creating what's called helicity. Helicity is, the term itself means the measurement of magnetic field twist in a given volume. And so by applying an electric field at a 90-degree angle, you're essentially forcing the plasma field to twist, and you're creating a twisted donut. And what's awesome about that is that you're heating the plasma when you do it, you're stabilizing the plasma when you do it, you're eliminating an instability that would have formed because you're working through the mechanism that the instability would have formed through. So you're eliminating it by doing that. And you're heating it up to the Mercer limit.
So that pretty much wraps it up. Really appreciate all the feedback. I hope that these question and answers clarify some things, and please email me, send me comments, send me feedback. I want to do more of these lecture series because this stuff it's not complicated if you have the right instructor, but a lot of times it's very difficult to get clear information out the door. And that's really what we need. We need to train up a workforce of fusion folks. And that's what I'm hoping to try and help and do here. All right. Hope you have a great day. Thanks. Bye.